Hey everyone, welcome back once again to the end of week 3 in our 4-week AirConf marathon. We're about to kick off things with John Scattergood. And John has 15 years of experience working in the maritime industry. And he writes and speaks a lot about a pretty interesting subject, which I find quite fascinating, uh, marine terminal automation. So I guess we're bringing together enterprise, robotics, um, code that really affects the world on a grand physical scale, and I guess not just at the dock, but all of the cool products that are being moved all around the world. So yeah, very excited to get a bit of an insight or catch a bit of a glimpse of what the life of a developer at this scale of engineering looks like. John, you want to take
Hey
it
everyone.
away?
Yeah, thanks, Jonathan. How's it going? Like Jonathan said that I'll be talking about automated marine container terminals. Now, the this is a very I would say a very industrial industry. And if you Can you roll to the next slide? So the company I work for is called Navis, and we're actually based in Oakland, California. We've been around for over 25 years, and we've been developing software for the maritime industry. Our primary product is what we call a terminal operating system, and it's kind of like the brains of these logistics nodes. Um, and we're a global company. We have offices all over the world, and we have customers in more than 50 countries. I just want to give you a sense of kind of who I work for and what we do. Um, Roll to the next slide, please. So a lot of you may not be aware of like what a container terminal is about and what a container industry is. So basically just start off like what we're talking about. So we're talking about like this thing called an intermodal container. So it is a steel container that comes in a variety of sizes, but the most common sizes are either a 40-foot or a 20-foot container. They're about 8.5 feet tall, but they come a little bit taller. And so this using these containers really revolutionized the industry. Back in the 60s, the industry was much more focused on individual parcels, and they would move things on pallets, and it was very slow. And so the industry really changed with the advent of trying to put all of the goods into a container of the same sizes, so they standardized on these size, and then they could create. Roll to the next slide, please. And so then they could create a container that could be used in multiple different modes of transport. You'll see these on the highways. These are on the backs of trucks. But you also see them on trains. They're being used there, and then they also see them on ships. And so really, when it comes to these containers, they've really allowed us to create a kind of global trade and kind of really add a lot of efficiency around the movement of cargo all over the world. So I don't know. Go to the next slide, please. So the actual just to give you a sense of like the business, right? How does it actually work? So let's look at let's talk about a story. Like, so we have Best Buy, and Best Buy, has TVs, and they sell TVs at their store. Now, in order to go backwards, yeah. And so Best Buy, they make TVs in China. So there's a company in China that makes a TV. After that TV is manufactured, it is put into a container. And so you see a couple pictures here, and then from that the container is taken to a port where it's put onto a ship. Now, to understand that there are a lot of different companies involved. This is not like FedEx or UPS where you've got a single carrier where you're basically dropping it off at the UPS office and then UPS kind of gets it to its destination. There are a lot of different companies in here. You've got the manufacturer involved. You've got the trucking company that takes it from the manufacturer to the port. You've got the port company that has to then take that container and put it onto a ship. The shipping line itself is transiting the ocean. You can see this kind of the circular path they make, whether they're going from the west coast of the United States over to China, They're stopping at a few different ports, picking up containers, and then they're going back to the U.S. to drop their cargo off. And so this carrier is another independent company that then takes on the containers. They will take them over to the port of discharge. In this case, it's in the Los Angeles area, the Long Beach, Los Angeles port harbor, and then they'll remove the container from the ship and they'll put it onto another truck, potentially, or to train, depending on where it's going. And then this container will be taken to a distribution center. It'll be taken out of the container, put into a normal kind of what you would see on the road, a freight truck, for the individual stores. And then ultimately, the TVs will show up at the store and be put on display. And so this entire supply chain has to be looked at as like the lead time from a retailer's perspective when they order goods and when they actually get them. And so sometimes that can be a month, and sometimes, or less. And so then when you look at it from the retail perspective, when they're purchasing and stuff, this is kind of the things that they look at. It's called logistics. Go ahead and roll to the next slide. So at a container terminal, it's really like the hub of like where a lot of this interchange of these modes take place. And so this particular terminal is in Los Angeles. This is Pier 400. Roll the next slide. So the terminal is kind of broken down into different operational areas. Obviously the first area would be the vessel. So in the vessel, they come and they berth at the port, and then all the operations to unload and load the ship take place at what we call in the industry the quay. Quay. And so it's basically just the dock, the pier where the ship berths. And so at the quay we have these massive cranes that are larger than buildings that are responsible for loading and unloading these ships. And these ships are massive. These days you can get ships up to like 18,000 containers in them, and they span the length of 4 or 5 football fields as far as the size of them. They're massive. So once in these yards, once the containers are taken off of the ship, they are going to the storage area. And so the storage area, there are lots of different ways of organizing containers within the yard. And so the storage area is where containers are stored and they're stacked for ultimately for delivery. So then we get to the next phase, which is the gate. The gate or the railroad, both of those things are in the terminal now. And so the gate, bring the container gate to go on the ship for going back to China, or they'll take goods that were dropped off from the ship to the distribution centers, either locally or remotely. Long haul cargo, railroads are actually involved, so we'll have what they call on-dock rail facilities. So they will transfer containers from the yard directly to a train, and then the train will be formed up outside of the terminal and will go to places like Denver, Chicago, New York, depending on what the final destination is. And so you really at this point, this combination of all these different things in one place makes it a really complicated problem. So traditionally, these terminal operations, they take place with very mechanized industry, but also very manual. So if you look at people everywhere, if you look at these pictures. So we have an example here in the upper left-hand corner of a container being loaded by a truck being loaded by a key crane. And in this case, we have people on the ground who are recording which container came off the ship and which truck that the container got placed on. Inside the cab of the truck, there's like a computer that tells the driver where to drive, where to go pick up the container from, where to take the container to. In the picture on the right, you see what we call a reach stacker. This is a kind of equipment that can put containers onto rail cars. There are lots of different types of equipment, and you'll see as we go through kind of how it works. But these are side access vehicles, and they can load containers into stacking areas, or they can go onto rail cars like this. The lower left-hand corner, you see the gate area. So you see all of these trucks that are queued up in this, looks like a massive toll booth. And in this area is where the trucks talk to people to figure out, okay, so I'm dropping off, I'm picking up, this is the cargo number I need, etc. And then on the right, you see you see a container being delivered to these trucks from a storage area with an overhead crane that we call a rubber tire gantry crane, RTG. The next slide. So, the industry is really under a lot of pressure right now. There are a lot of demands to increase productivity. We have the shipping lines for building much larger ships, and these ships, they want to get turned around in the same amount of time as the previous ships. So the demand for higher productivity from the terminals is really putting pressure on them. There also, the operational costs of terminals are going up with regards to personnel and equipment to be able to staff these terminals. There's security pressure. Terrorism after 9/11 and preventing terrorism has had a lot of impact on, like, tracking cargo and what's in the cargo and where to come from and how do you inspect the cargo and how do you make sure that people don't have access to the cargo. These are all concerns. The other thing is safety. Like, people that are involved in these actions, because there's such a small space between people and this large mechanized equipment, it's very dangerous. And so the focus on safety, making sure people don't get hurt, this is ever increasing pressure. And can you go back to the slide one more? You'll jumped ahead a little bit. Yeah, and obviously we've got visibility as an issue for the throughout the supply chain. So what a lot of these retailers and manufacturers want is they want to have a very lean supply chain. And so in this case, they want to be able to have what they call just-in-time ordering, or they want to try to keep as much little inventory in their warehouse as possible. And so in order to, they have to have visibility about where the cargo is at any point in time. And so the pressure to provide that visibility means that terminals have to be a lot more accurate about where how they track containers, and they can't lose containers, so they have like 100% accuracy about locations and things like that. The next thing would be environmental concerns. So the current carbon footprint of these terminals is quite large. All of the equipment in a traditional terminal are powered by diesel or gasoline, and they have a lot of emissions, as well as the over-the-road trucks. The trucking company, the trucks you see on the freeways, also are going to the terminal, and they have the emissions. And so the longer that they are at the terminal, the slower, the longer the lines are, then the more costly or the more environmental impact there is. But when we talk about reducing that, I'll show that with automation comes a lot of opportunities to be green, because you can implement a fully electric system without having a lot of CO2 emissions. And lastly, competition between ports, between regions, is always there. And so as terminals kind of have a one-upsmanship with regards to innovation, they all have to keep up, or otherwise they'll will not be in a competitive place. So this causes all these terminals to focus on automation as a way of providing a solution to each of these pressures and alleviating them. So next slide, please.
Just to quickly interject, what you're seeing on the slides isn't always what's showing on the camera. The camera is focused quite a lot, so sometimes with the slides like a little bit ahead, don't worry too much if it's like.
Okay. No problem. So the operating costs, just to give you a sense of like the operating cost of a container terminal as a percentage of the costs for each of these areas that I had mentioned before, and most people wouldn't. Most people would have been not aware of this. So the primary thing is that the personnel costs, and these numbers are taken from like a terminal in Northwest Europe, but personnel costs of these sites is significant. And then the next biggest costs are the capital costs of the equipment and the facility and stuff. So So anyway, just to give you a sense of like what the terminals are facing and how automation can really help reduce that. So next slide. So the drivers of automation are primarily that we want to be able to reduce the labor costs, as I mentioned, but automation also provides a reliability of operations. So the automated equipment, they don't get tired, they don't need breaks, they are always operating if they're maintained. Then so they don't go on strike and things like that. So they're, from a reliability perspective, they're much more reliable than people are. The next one is that when you add automation, you have an opportunity to focus on optimized logistics. And so basically, because when robots, they don't have eyes and ear and brains, right? So they have to be, the systems that run them have to think for the equipment. And so this is an opportunity to write some sophisticated algorithms deciding, how the equipment should be used, and then from those decisions, you can actually optimize the cost of the fleet by figuring out the best usage of the equipment. Obviously, there is an improved safety with regards to automation because we separate people from the robots with fences, and so you don't have to have people involved, and they can use cameras instead. And so ultimately, because they're robotic, they're able to execute work without endangering anybody, which makes it really a great improvement for safety. And obviously, like I said before, there's a lot of reduced environmental impact because these automation technologies are all electrified. So we want to make sure that with the electrification of the yard, it really reduces the CO2 footprint, which is a big environmental improvement over the current standard. And then lastly, reduced maintenance, and that's it may be seem like it's counterintuitive, but actually because the robots move containers more consistently, they're able to do it in a more consistent manner with less, like for example, a person might lower a container from a crane too fast and will create a hard landing of the container onto either the ground or to the container below, and that has a big impact on the container equipment, but also on the handling equipment as well. And also, if they are raising the container too fast, they can put strain on the various cables and the devices that are used, and so that will ultimately lead to more costs when it comes to repair. But because the automation is consistent, it actually reduces the overall maintenance costs over the lifespan of the equipment. Next slide, please. At container terminals, there's actually a automation progression. So there's different levels of automation that terminals can add. And so the first level is like this decision automation, right? So we need to think about, okay, so where are people involved in the decision-making processes at the container terminal? So just to give you a few examples, it's like I need to decide where containers are going to be placed within the storage area, and organize. How am I going to organize the storage area? Now, a long time ago, you'd have to actually make those decisions based off of paper and experience. But now we have algorithms that can decide that on the fly and make a much better decision over people, and so that automates that decision process. The same goes for stowage planning for vessels and trains to figure out what's the best place to put containers on the ship so that they don't so they have the efficient cargo transfer at their next port of call. And equipment usage. So these are like the cranes in the yard and the trucks to actually decide which work that these equipment should be doing, and then instructing drivers to do it that way will allow us to optimize the usage. If you can imagine, if you just take it out of the terminal and you think about a delivery route, like the delivery route of anything, like papers or whatnot, or goods, you want to try to drive the shortest distance. And so a lot of these decisions, are not obvious to an individual driver, so you need kind of a higher level of control, in order to get the most efficiency out of the system. So the next level is process automation, and so the process automation is around using hardware to do different things. And so we talk about accuracy at the first level, and so when we talk about accuracy, we're talking about position detection or GPS to track the locations of containers. And so this takes the human element out of it. So when we move containers around in the facility, we can actually track where the containers are going precisely, and so the driver doesn't have to tell the system where he put it. It's just automatically known. And also, because we're using instrumentation, there's no cheating, right? So we can precisely know where things are, and we can always go back and find them. The next thing would be around reefer monitoring. So I put that as far as the accuracy. So when we have refrigerated containers that in the industry call reefers, these refrigerated containers have to maintain a certain set temperature, and if they don't, they have to be repaired. Otherwise, it can totally destroy the goods in the container. So they have the ability to monitor them, and so there are actually mechanics who are employed to go and check the temperatures, but of all the containers and inspect them all in the facility. But we can actually do that automatically now, and so the automatic temperature control and automatic temperature monitoring allow you to get accurate readings about the current temperature, and so then that can be fed into our system that we can then make sure that if there are any deviations that we can then, upon exception, send a mechanic out to figure out what's wrong with the container. On the accuracy, on the data entry side, really talking about taking people's fingers off the keyboard. So through barcodes, RFIDs, barcodes, RFIDs, and OCR, we can actually capture container information, and so this allows the terminal to reduce the labor required to enter data and the mistakes that are required, and so you can actually speed up the processing of data and reduce labor costs. So anyway, the basic thing is that the process automation is a big area, and neither of those actually require terminals to change their operational mode. So the last area is really what I'm going to focus on, and so the last kind of level of automation is about the equipment themselves. And so on the equipment, we're talking about robotized equipment to move containers. And so in this way, we have different types of automation that we can employ. We have the automation for the stacking cranes, for the cranes that are moving containers in these storage areas, and we have secondary to that we have the transfer of containers between storage areas. Is that transfer happening with automated equipment or manned equipment? And then we can apply this in other areas, such as we have one customer who has these massive cranes that are moving containers on and off the ship. Traditionally there's a driver in those cranes who are making those decisions. We have one customer who's now going to complete remote control for those cranes, and I'll show you a picture of that. So it's not completely automated, but it's remote controlled. So it really takes people out of the cab of the crane and really puts them into an office, much more comfortable environment to work in. So when we talk about automated terminals, there are a few different ways that these terminals are laid out, and some of them are similar to the way that we lay out a manned terminal, but some of them are very different, especially the ones that we've seen a lot of. So the left-hand side, you'll see a picture, and these are what we call end-loading automated RMG sites. And so basically the cranes have basically a rail track that runs around along the sides of each of these storage areas, and then these massive cranes, which can be 40 to 60 feet high and 80 feet across. They're massive, and so they will have multiple cranes, usually two, that will share this track and manage the storage area, and then the transfers of containers will happen at the end. So you'll have one transfer area that's close to where the ships are, and one transfer area that's close to where the trucks are. Alternatively, some sites have chosen to do kind of a side loading concept, where the storage area is parallel to the berth, and all of the transfers take place on the side rather than the ends. But these sites require a lot of well, let's just say they're very difficult to fully automate. Most of the sites that use this layout are semi-automated. They'll use an automated concept for the storage area, but all the transfers are done with people. And so they have an interchange between robot and people that I'll show you later. The next concept is kind of a different one. Is one type of equipment in this concept is called a straddle carrier, and the containers are arranged in rows, long rows, a single container wide. And then I'll show you a picture later on. But there's one type of equipment that's responsible for moving containers from the ship to the storage area, and then from the storage area to the trucks. The last one is similar to the side-loading RMG concept, but these are uses rubber-tired cranes, and the biggest difference here is that obviously cranes that are on rails can't move off of their rails, but a rubber-tired crane can actually move, and so you can redistribute the equipment in the yard based on what's going on, and so it adds another level of sophistication to it, the operation, by being able to move the yard cranes between storage areas based off of the demands. Next slide. So as I talked about, we have this end loading concept here. You can see a couple pictures here. These are from sites that we have around the world. So up in the left-hand corner, this is a site that's in Dubai, or sorry, the United Arab Emirates, around Abu Dhabi. And so this site has these robotic cranes that transfer containers on the end, and these sites use what they call a shuttle carrier to do the transfers, and so you can see a picture of that. So it basically carries the container between the legs of this equipment, and in these sites, these shuttle carriers are run by people, so they're actually people that are using the kind of transfer mode. And so the main point in these facilities is that we call them kind of semi-automated, because only one aspect of moving containers is automated, and those are the cranes. In the upper right-hand corner, that's a terminal in London, UK, and then the lower left-hand corner was a terminal in Antwerp, Belgium, and then on the lower right is the terminal in Portsmouth, Virginia. So the first American site to use automation and container terminals. And in this picture, you can see how the over-the-road truck can park next to the transfer area. You can see that they're in there now. You can see the street trucks will park back into this area, and then the cranes will transfer containers. Next slide. So in this concept, these are again end loading, but in this concept they use robotized equipment to transfer containers, and so these are called AGVs. And so the containers are placed directly onto these AGVs, and then they're driven around the yard to transfer the container from the storage area to the ship. In the upper right-hand corner, you can see this is underneath the crane leg, the key cranes at the ship side, where these containers are waiting for load. And then the empty ones are waiting for discharges, containers coming off. And so you can see how it's very congested, but we have sophisticated software systems that can kind of manage this congestion and track where these equipment are and the routes that they're going to take. Next slide. So when we talk about what is a terminal operating system that we provide, it is really the center or the brains of the container terminal, and we have a lot of other systems that connect to the terminal operating system in order to make the whole terminal function. And I'll just talk about each one a little bit. So the terminal operating system is connected to, I guess, first and foremost at these automated terminals, some type of equipment control system. And so when we talk about like what the differentiation or what the dividing line is between what systems are responsible for, the equipment control system is generally responsible for navigating the equipment, executing the orders that we give them. So the kind of orders that the terminal operating system is going to give us is say, please, request to move a container from this location to another location with this priority or whatever. And then the control system will then take that kind of abstract order and then convert it to, okay, crane needs to move to XY coordinate, needs to lower the spreader and lift the container up and then transfer it to this other area and lower the spreader down. So these kind of micro control actions, the terminal operating system doesn't get involved in that. It kind of deals with a more abstract level. And then the control system integrates with different types of equipment. So there may be a different control system for the guided vehicles or a different control system for the cranes, and so they have to coordinate for handoffs and such. The second one will be like a key crane automation system, and so like I talked about with regards to remote control, but there's also deals with the fact that we have some cranes that have partially automated. So the drivers, in the olden days, well, I say the olden days, but there are a lot of sites that still do this, but the driver is responsible for completely the entire move. It'll pick up a container from the dock and put it onto the ship, and pick up a container from the ship and drive it to the dock. These days, what we can do is we can advise the crane system, like, this is where the container is supposed to go, and so the driver really is responsible for the last 10% of the move. It will connect the container on the dock, and then he'll push a button, and then it will automatically move the container over to the ship, and then wait for the operator to kind of finish it off, because he can use his eyes to kind of figure out positioning. And so it can really increase the efficiency by reducing the need for the crane operator to make those long moves, because there's a lot of physics involved, because these are very heavy containers, they're very long distances, there are lots of problems with sway, where the container will swing back and forth. If you just imagine you're holding a barbell on a rope, and you try to move the rope at the top of, hold the rope at the top and move it, and look at what happens to the barbell at the bottom. Well, the barbell is first, going to be behind the rope because it's got more mass, and then as the barbell starts to move, as you stop holding the rope, the barbell is going to keep going. And so you got to compensate for that. So what these drivers, the very skilled ones, do is they'll start moving, and then they'll kind of back off, and they'll kind of make it work that way. And so now we can do that with robotics. And so you can really deal with these physics problems. Just to kind of go around a little bit, we have reefer monitoring systems that I mentioned. We have financial and accounting systems. So every customer wants to get paid for moving containers, and so we have the ability to connect and find all the movements of a container that took place, and issue invoices, and then you have to collect on those invoices. All that stuff has to happen. We have partners that deal with the terminal, the shipping lines and the shippers, and anybody who wants to know what's going on with my container, has to be able to get access to the information. And so, we use these kinds of industry standard EDI formats for that, which is just basically a flat file that has some formatting, and then also we have web services and stuff that people can use, and a web portal that people can use it depending on what they need. Customs, every country has a different customs process and a customs system, and so each of those have to integrate with our system. Some sites are in large port communities, like say for example the Los Angeles and Long Beach harbors. There's 10 or 20 different terminals down there, and they all kind of coexist, and so you have these community systems that are trying to help truckers figure out where they're going to go next and answer questions about availability. So a lot of sites that have these community systems have to go to each terminal and get information so they can aggregate it and create a portal for the constituents. Sometimes we have an appointment system that tries to say, for trucks that are coming and picking up containers, when they want to come. It helps us optimize how we're going to order how we're going to restow the containers so that we can create efficient appointments. And then lastly, these gate operating systems. And so I'll show you some pictures here. But basically, it's like when trucks come in the facility, they have to get a lot of information recorded. They have to be processed in a queue to efficiently handle them. And so there's usually a subsystem that's responsible for that kind of processing. And then they will feed information into the terminal operating system. Okay, go on next slide. Okay, so in general, just the high level, within that TOS circle, like what is the general responsibilities of a terminal operating system? And they're like kind of like we have thousands of micro features, but at a general like responsibility perspective, it really falls down to these kind of 5 categories: resource planning, trying to figure out how we're going to use the yard and the storage in the yard, figure out how we're going to use and allocate the berth, because we got ships coming and going. We got to make sure we know where we're going to put them on the berth, what time they're going to be there and such. The stowage of the vessels, like how are we going to use the space on the ship to efficiently load the containers and discharge them. Rail car stowage, again, a very similar but different process. Track allocation would be regarding to rail cars. So if you remember that picture of the terminal, there are multiple rail tracks at the facility, and so we have to really decide, okay, we have a train coming in at 8 and a train coming in at 10 and a train coming in at 1. Okay, which tracks are we going to do? Like which ones are coming and going, and trying to figure out what's the best usage of those tracks. And then the key crane assignments, the ship-to-shore cranes, figuring out which cranes are going to be assigned to which ship at any point in time. How many people are we going to use for this particular work, and then organizing that so that we can maximize our berths and the cranes that we're going to apply to each vessel. Kind of an obvious one is inventory management. Obviously, we have to track cargo, but we also have to deal with cargo control. So we have customs and different ways in which containers can have to be put on hold, can't leave the facility, or they can't move, or maybe they need a permission to then perform an activity. And then obviously we have to deal with the opposite, which is kind of a release process. So a customs puts a hold on a container because they want to inspect it, and then they'll send a release that gives it permission to leave the facility, kind of thing. All that stuff has to be managed. Order management is another area. So we have to deal with kind of manifests of the ship and trains, and then bookings. So we have to say, like, the customers, the shipping lines will tell the terminal, okay, so we're expecting to receive 40 containers for this port of discharge, or say for Hong Kong, for example, 40 containers for Hong Kong for this ship. And so then when the trucks come in, we can allocate the containers that are coming in against those particular bookings, and so we can kind of cross off what we expect to come for a ship versus what's actually shown up. Kind of think of it like airline tickets, right? So the airline industry is like going to issue tickets for a plane. It's very similar in the sense that, but it's kind of more generic in the sense like saying, well, we have a group reservation for 8 people, but we'll tell you the names of the 8 people when they actually show up, but we're only going to send 8, so kind of like that. Then we have to deal with like receival and delivery. So we have to cross-check. So all the containers that are coming off the ship or going on the ship or coming in and out of the gate, that process about interchanging, we see it as a kind of a software artifact where we're actually just, changing the location of a container, entering in some information, but there's actually legal things that go on behind the scenes when you receive responsibility, liability for the cargo, and you have to go through the process of kind of implying that by going through the software to transact those containers and then audit what's going on. And then obviously there's like general service requests. Maybe they want a container washed, or they want it cleaned out, or they want to put something else in it. Some sites have, some terminals do more sophisticated type of services to prepare containers, and so they can charge for those, and so we have to do some kind of management of that. The next area is like a really big area, even though it looks similar. It's like really equipment control, and that is monitoring the operations. It's managing the allocation of equipment, like we talked about before, the allocation of equipment to do work, and then about decisions about scheduling and dispatching of that work. And as the work is taking place, we need to have some kind of workflow management, so we can actually be able to figure out and communicate to the entire terminal like what's going on. So when a container is being issued to a driver to go and pick up the container, or to a crane to pick up the container, we want to track the process, right? So they accepted that instruction, they're going to go pick it up, we're going to update the location as they do that, we're going to kind of show what the current status is. So all that workflow management, like what's going to happen next in the process, has to be kind of defined, and then exception handling. So when things don't go right, which is very often the case, you have to have like a decent exception handling system to be able to accommodate things that go wrong and be able to propagate those errors to users, and then have processes to kind of get them out of that situation. And then lastly is a general integration. We have to integrate with lots of different parties. As you saw from the previous page, we have to integrate with lots of different parties and different mediums, and provide reports and things as well. So that's another big responsibility of the terminal operating system. So this is just an example of like some users in action. So these are people using our software in the field. You can see like in the upper left-hand corner, people are like looking at a vessel plan, and they're looking at some camera images from the key crane. We have a person using a tablet to kind of look at the status of a cargo. In the lower left-hand corner, we have somebody who's monitoring the operation to see what's going on, and talking on the radio to figure out who's going to go look at an issue. And then on the lower right-hand side, these are what we call clerks. These are responsible for talking to truck drivers and figuring out how to get them through the facility, and basically servicing them so they get to bring the containers in that they want, that they need to, and then get the containers out. So like I talked about before, there's like a number of different areas where automation can be applied. So I'm just going to go through like kind of a series of areas where we use automation, and so you'll get a sense of kind of how we apply automation to container terminals. So talking about the gate, this is where the trucks come in. We have a lot of sophistication here to automate the process of data entry. And so you'll see like this is a picture of like a camera system that's used to take pictures of the numbers on the container, the numbers on the truck, the pictures of the driver, looking at the doors of the container to see if there's a security seal attached, actually looking and seeing whether there's damage on the container, because again, like I talked about, there's like intrinsic liability. If you want to receive a damaged container, you have to know that it's damaged. Otherwise, you're assumed that you damaged the container, like you would say a rental car, right? So same kind of process. So they do an inspection, and these use cameras to do it, and they capture that. And so in the upper right-hand corner, you can see kind of like the process, like the aggregation of all those pictures, and then it can really identify, like it reads the license plate, reads the container number, it knows the lane they're in, and it can actually cross-reference that with what we expect to happen. So a lot of sites, they'll do pre-advisals about what's going to come. They've got the booking information, so they can kind of match it up against the booking, so we know that this container is going to come, and so they can kind of reduce the amount of data entry that's required. Next slide. So on the railroad, kind of a similar process, but a little bit different. We've got, again, like this camera system. On the right-hand side, you'll see this camera system that's taking pictures of containers, because we're trying to automate the inventory process. So as the train is coming in the facility, we want to capture which containers are in which positions on the train, and which order they are. So, because if you don't do that, then you can never trust the manifests from the railroad 100%. You always have to double check. Same with the ships. So when the containers come in, you want to cross-reference what containers are coming in, which are supposed to come in, and then from that process I can begin planning. And so normally, without this system, you'd have to have a person who would have to walk the track with a mobile device to record which container numbers, and it's very time-consuming, or on which rail cars. This process completely automates that. On the lower left-hand side, we've got this picture of like every rail car has like an RFID tag, and so you can have readers can kind of read the order of the cars that they come in, and then things like that. And the upper left-hand side is the new site that we're involved with, and this crane is going to be like a semi-automated rail crane, and so the rail tracks go underneath of the crane, and then the driver sits in the cab, but basically he's only there for safety purposes. Everything is pretty much automated. He just has to make sure that the thing doesn't hit anybody. And so that's kind of a new concept to be a fully automated rail crane, mostly because the positioning of the rail cars is variable. Obviously they're on wheels and they move, so being able to track the location of those cars on the track is really important. Next slide. So this is the key where the ship-to-shore cranes are, and there's a couple of different interesting things here. So first and foremost, like if you look in the upper left-hand corner, I kind of circled a picture there of a camera. And so these cameras are taking pictures of these containers, and these containers have numbers on them, and so then they can correlate to the containers that are supposed to come off versus ones that aren't supposed to come off. I mean, they're trying to validate the manifest of what's supposed to be discharged. And so without the cameras, you have a person who has to read the container number as it comes off, and we do something like a double. When a person is involved, we do like a double blind entry. So they enter the container number twice to confirm that this is the real container supposed to come off, and that ensures that they have the accurate number. But that process is time consuming, and so we want to automate that process. So we have these cameras involved. In the right-hand picture, this is a different type of crane. This actually has two cranes in the same frame. So there's a main, what we call a main trolley, which is responsible for moving containers to and from the ship. And that main trolley puts containers onto a platform. And then we have a secondary trolley that moves the containers from the platform to the AGV. That secondary trolley is completely automated. So it goes based off of the flags that we maintain about whether the containers are ready to transfer on the platform or not, and so then it'll just automatically move them to the so the key crane driver doesn't have to think about that aspect of the automation. Underneath of that, I have a little screenshot of like a GUI that we provide. The first top block is what's on the main spreader. The second block is on the left-hand side is what's on the platform, and the third block is what is on the secondary trolley. And then on the right side is showing which AGVs are in the lane and with containers. On the left of that, we have a screenshot of a very happy person who is remotely controlling a ship-to-shore crane. So. So this is that example of that remote control of the ship crane. You can kind of see the camera angles that they're seeing, so that they can actually perform this operation remotely. Next slide. So we're getting more towards the yard now. Yard automation, where we're talking about the cranes and the AGVs themselves. So just to give you kind of sense, like, so we've got these cranes, and like most of them have these sophisticated laser systems to be able to calculate what the stack profile is, because they want to be able to safely move containers around. And so by calculating the stack profile, they can actually optimize the motion of the container as they lift them around. And so what you don't see here is also, for example, they have like a number of other systems that are on these cranes to track the location on within the stack and to do position corrections and anti-sway for moving these containers around. On the right-hand side, you kind of got to try to get a picture of this, but these AGVs actually have this transponders in the cement at the terminal, and they can use these transponders for navigation. And so it's much lower tech than, say, a radar or LiDAR or anything you might see from the DARPA challenges. Basically, because it's a controlled environment, they just put these transponders in the concrete, and then the vehicle will drive over the transponders to maintain location and also know which transponder it's over and such. Beneath that, it's a picture of a remote crane operator for the crane in the upper left-hand side. And so you can kind of see they're in a control room, and they're looking at these camera images to kind of figure out how to load the container onto to do the transfer of the container to a truck, for example. And they're trying to match it up with the pins that are on these metal frames we call chassis. And then the left-hand side, just trying to draw a picture of this, is a waterside transfer area. These are what we call basically they're like electronic barriers. These are lasers that are shooting beams back and forth, and they're on two different angles or two different dimensions, you can say. So based on the way that curtain, that light curtain, is broken, you can tell if something is coming into the transfer area or leaving the transfer area. And so we also have a light system here. So if drivers are interacting with this, in this site is actually humans that are driving equipment in here. They can see whether they should stop or go, and if they can go, we can know when they're in the zone and when they get out of the zone. So what I want to talk about is like really there's like layers of systems involved in these container terminals, and it starts at the very, very low level, like the mechanical and electrical level of these equipment. We're talking about the motors and adjustable drives that go into moving the containers. And then on top of those, you build in these transponder antennas and wheel counters and lasers and GPS systems. And then we get into real software that leverages those sensors, these onboard systems for positioning the crane and for controlling the crane remotely, these the remote control capabilities. And then a diagnostic system that can detect faults and then communicate that back. Then those cranes are then wirelessly connected to a data center that will then be able to centralize the faults and diagnostics for the entire fleet of equipment, and then provide access to a remote control console so they can connect remotely to these equipment and drive them if necessary. On top of that, we have this kind of higher level of sophistication with this middleware. So some sites use this middleware called an ECS, the equipment control system, and some sites they don't use it depending on the level of sophistication. But basically this middleware is about integrating multiple types of equipment in the yard to do equipment coordination. So if you look at some of the other pictures that I showed before, the automatic cranes need to connect with the automatic vehicles, and so they have to have this coordination. And so this system is generally responsible for ensuring that they're coordinating those transfers. Above that, we have like our system and what we do. So we have like user interfaces. Obviously, but we're responsible for job planning, inventory control, scheduling of the work, and then job selection, which we then pass down through that chain. Next slide. So, one thing to notice is that with the layers of systems, equipment failure should be expected. Like if we look at our traditional like kind of reliability formula or availability formula, we have the mean time between failure divided by the mean time between failure plus the mean time to recovery times 100. That'll give you your percentage of availability. So if we really want to calculate like what's the probability of any one failure in the system, you have to add the probabilities together. And so with these equipment, we have like on average, and that means we have like 60 or 70 of these AGVs, and we have 60 or 70 of these cranes that are interacting. And so that's over 100%. Even if you have like 7 nines of availability, you still get there will be at least one failure at any one time. So you kind of have to design your systems to kind of deal with these failures as a normal part of your procedures. And so that adds a lot of complexity, but it's something that you have to be aware of, is that there will always be something broken, and you will not be able to know when it's going to break. So you have to design in this kind of reliability up front. So the challenge in building these systems really are trying to deal with these opposing odds. And so, when we talk about like we need reliability as our foremost, we need consistency across the system. We need some level of determinism so that we can reason about what's going to happen or what did happen in the past, and we need to ensure maintainability. So all of these needs, these attributes, to get them, you need to have a simple system, to simplify as much as possible. But at the same time, you have these opposing kind of requirements about providing a lot of capability. So that we can handle like hundreds of different use cases and support lots of different operations. And so adding a lot of capability means you've got a lot of opportunity for bugs, a lot of opportunity for testing, or a lot of need for testing and validation. Also, because we develop a product, we have to provide a significant amount of configurability because we have different customers who have different needs. And so the configurability by itself, it can add in another code path every time you add a configuration, and so it just multiplies that complexity out. extensibility is also a big concern of ours. So we have a number of customers that will take our base system and then extend on top of it. So we have a number of ways that we can extend it. And so that creates a degree of freedom that adds into the complexity. And then obviously we have to scale the system. And in order to operate at scale, you have to distribute. And so in order to distribute the load and be able to handle the different terminals of different sizes and loads, that adds this idea of obviously at the lowest level concurrency, at the highest level distributed computing. And so all that complexity is increased by adding that. And then I added performance at the bottom because, you know, in order to get good performance, you can argue I need to simplify the system, but the other one is to say that in order to get performance out of what I have to make it more complex by adding caching or any other kinds of things in order to speed up the algorithms. I have to, and by adding in caches and pre-calculations and denormalization of the data, you are creating complexity. So this is a real challenge for these systems. So, I mean, I'm going to talk a little bit about kind of what we've done to kind of, but I just wanted to share, like, you know, my impression of building systems like this, and how, you know, as you get to this kind of level of system, you really have to kind of deal with these types of challenges. So, you know, I get a lot of like heat from people for talking about and bragging about monolith here, but you know, there's a lot to be said for well-structured monolith. And so what I mean by monolith is that we have a single application that is running, and it's a Java web application, and everything is in the same Java web application. It is well structured and modular in its core, but it allows you to do a number of things that you wouldn't have to worry about otherwise. So first and foremost, it's a product. We're selling a product. So we want to have this install very easily. So when we can ship customer basically a bundle Tomcat with our web app and say, hey, go install it, and if you need 100 of them, go install 100 of them. It doesn't really change the process. You know, a lot of the customers we deal with are in the third world, and you know, and IT infrastructure is more difficult to come by, and training is more difficult to come by. So having this kind of ease of installation and ease of monitoring, because you really have to monitor one thing, is really a tremendous benefit. So. So then we also have the concept that this well-structured application is also easily fungible. Like, there's no single point of failure. We try to keep them stateless as much as possible, so that if any one node in the cluster fails, it can be taken over by another node without having any impact to the system. So you kind of get this kind of Borg thing going on, where like you can, if a server is going badly, just shoot it and restart it, and it doesn't impact the system. And so that's really what we're trying to do. So we have a well-structured monolith that's stateless, that uses a relational database because it's highly consistent, and we're able to provide a very robust solution to our customers. The other thing that's really important is to create standard interfaces, and this allows us to reduce the amount of testing complexity, but also it allows us to really focus on facilitating predictability with what's going on. So we have standard interfaces for dealing with automated equipment. We have standard interfaces for dealing with manned equipment. We have web services that use RESTful web services, and more older SOAP-based web services that we use for interacting with various systems. And by just having a standard allows us to kind of maximize the investment that we make in these interfaces. Next slide. So, you know, this doesn't represent our entire architecture, but it focuses on kind of the main things for automation. And so what we've done internally within our application is kind of break it up in decoupled components so that they aren't tightly talking to one another. So we have all of our messages coming in from control systems coming through our enterprise service bus layer, and they're abstracted into events. So we never deal with message specifics inside the system. This allows us to insulate us from different vendors who have different formats that we may need to convert from or to. And so we do that all in the interface layer, and then we deal with this abstraction of events. These events then pile into, so then we're trying to have these events pile into our workflow system, which then processes these events and figures out, okay, the crane moved here and it's doing this activity. It then deals with these business APIs that are highly, highly set up so that they look like real APIs, and they call into them through, through a good defined interface, and then those APIs then deal with persisting data, and so it's kind of a very straightforward thing. And so then we also have the persistence. As things change in the system, those persisted changes are then also republished out to this event bus, and the event bus, the interface itself is listening for changes on the event bus, and then we'll say, oh, okay, well, something changed. I need to tell the other system that something changed. And so in this way, we can propagate changes in and out of the system without any one component knowing about the other. It's been really a good benefit for us in this fashion. On the optimization and dispatching side, we actually have a slightly different process. Go back one more. If it, I don't know. So anyway, so we have a slightly different process in that we try to pick a strategy that would give us a robust calculations that have fault tolerance. So when we do these optimization jobs, we actually do them as part of like a clustered background job, and so we'll basically distribute these algorithms across the cluster, and then once they're finished, we'll persist data, and then they'll run again based on their schedule. And so regardless of, we went the first time we tried to make all this optimization event driven, and we really found that it was hard to find the right business events to run optimization, or when to trigger optimization. So instead we just went with this very simplistic approach that, well, the optimization is going to boot up and run on a frequency, and we'll look to see whether it needs to do another optimization run. And in that process, you try to make that really the check to see, should I do another run, make it very efficient, so that we can just basically add on to the system and add different optimizations without having to couple them to the components that they may be running against. And so this allowed us to have that fault tolerance, because if a job failed to execute on one node, we rescheduled on another node. Next slide. So one of the hardest challenges that we have in this area is around optimization, and primarily equipment scheduling. And just to show that we have got multiple vehicles with multiple timelines that we need to orchestrate to effectively move containers to and from the ship with as few amount of equipment as we can, and also meeting the tight deadlines that have been prescribed. So we've written sophisticated optimization algorithms, and we use an optimization engine to then calculate what the best combination of things are. And so really this problem is what is what we spend a lot of time on to kind of tweak and tune to get to the right kind of execution level. And it's also kind of where we have a lot of experience. This is actually our third generation of a lot of these algorithms that we're kind of working on. Next slide real quick. So the goals of these scheduling algorithms are, first and foremost, we're going to maximize the productivity of the ship-to-shore cranes. So anytime the ship-to-shore crane or the key crane is not moving a container is a lost opportunity. So we have to make sure that we can feed those cranes without any delays. The second thing is, which goes into this minimizing the wait time. So no waiting. So we want to make sure the cranes aren't waiting for vehicles. We make sure that the vehicles aren't waiting on the yard cranes, and vice versa. So then on the bottom, we're trying to also maximize the resource utilization so that we don't have an oversupply of equipment to one crane, and it ends up happening to, by accident, starve the other crane. So we want to make sure we have resources are balanced in a way that that can achieve the desired goals within those constraints. Next slide. And like I was saying before, when we've really focused on these optimization jobs, we've really tried to look at how do we create kind of a compute cluster within our existing application. And so we've been able to categorize predicates around what these optimization problems, how many cores they need, how much available memory does the system have on each node, how do I want to segregate my nodes into groups, so that I have made some nodes that have more compute resources, like faster CPUs or more CPUs over on these nodes than others, and so we want to isolate the optimization in those areas. So based on that, we can actually, because we have this job scheduling concept, we can actually efficiently figure out where to run different optimizations based on what we have, resources we have available. Next slide. So the other thing we had to do for building our product is find a very clean way to open it as a extension platform. So one of the things we have like our core application is written in Java, but we have a plugin system that uses Groovy. And Groovy is a JVM language that lets you interpret it dynamically, and so it has a little bit different syntax in Java, but you can kind of write Java syntax for Groovy. But the idea is that customers can then write extensions using Groovy, and then have those extensions be plugged into our system. And so you can extend the system by adding your own web services. You can have your own background jobs. You can create custom events and notices. You can create custom workflows. You can add business logic. You can extend our system and just augment it, or you can replace components in our system. And this includes optimization. So if, for example, that our out-of-the-box optimization solution is they need to do something special with it, they can replace it with a third party, like that may want to come in and do an optimization for replacing something that they don't like from us, or if they want to do optimization in areas we don't offer a solution. And so this has really been one of the big selling points, is that we have a complete terminal operating system, but we also have it's a platform for extensions. So our approach is a product approach. Like, we don't treat each site as an individual project. We don't have forks of our code for each site. We have a common product that offers a high degree of customization and configurability. And because it's a product, we can optimize testing, we can optimize deployment, we can then optimize support and maintainability of that, and then everybody has a kind of a benefit. So if I have 100 customers who all are asking for features, and I develop a feature for one customer, or I develop a feature based on that input, then all customers who upgrade are going to get that feature. So you can kind of create a kind of a sympathetic system where you have, or a symbiotic system where one site's helping the other site. Even though they may be competitors, they're both getting advantages from each other. So, kind of just to reiterate kind of our goals. So the goals of our system is to provide an integrated solution with, top to bottom, so that we have worked with the vendors, we have tested with the vendors, they're providing all the equipment automation. The customer can feel confident that everything is going to work. There's so many different components involved. The last thing that they need to think about is making sure that the different parties involved are talking together correctly. So we try to provide that system for that. We want to provide a fault-tolerant system, because if our system is not running, the terminal is losing money, and so we have to do our best to try to provide the ability to deal with faults in a way that will allow the system to stay running. We have cross-platform, so we have to support Windows and Linux environments with the same product, and so obviously we're Java, so that's usually not an issue. But we also deal with different databases, right? So we have to support Oracle and SQL Server and various different relational databases to kind of deal with that. We want to provide modern interfaces using web services wherever we can, but we have the capability of doing, with some of the control systems, we do a database-oriented interface. But with regards to the capabilities, we have the capability of doing very modern interfaces, either through messaging like JMS or through web services. We have to provide a scalable product. We also, I didn't get into this, but we also have to support the idea of a multiple facility deployment. So we may have a site that has, or customer that has 3 terminals that they want to run the same system on. So we have one of those terminals might be an automated facility, and the other 2 terminals might be completely manual. And so we can't have this kind of global view that, okay, so everything is the same across terminals. So we have this way of creating kind of a multi-tenancy environment within our application and make sure we don't do anything architecturally to violate that multi-tenancy concept. Obviously, I touched on configurable and extensible earlier, but lastly is virtualizable. We really are committed to allowing our customers to use virtualized hardware, so we have to use that as one of our core design concepts, that we're not doing anything that prevents customers from using virtualized hardware, and so that's kind of one of our goals. So my last pitch is you're hiring in Oakland, and you can check out what we have. We have a number of software engineering positions open. We actually even a JavaScript front end guy we're opening for. So please come and take a look at what we're doing, and I look forward to hearing from you guys. So just the last slide is just my own kind of a plug for myself. So this is me. I'm on Twitter. I'm on LinkedIn. You can catch me there, or you can find me on AirPair.
Wow, thanks. That was awesome. How did you get into this in the first place?
So, well, first of all, I graduated from Maritime Academy. So I've been in the industry since I was in college, sailing on container ships and working container ports. But I've always kind of been focused on the technology side of it. So I just got in early, and I just got the bug. This is a very addictive industry because, I didn't say it in the presentation, but, you really can affect the world with your software, because 40 to 45% of the entire cargo throughput of the world goes through our software. Everything that you have in your house at some point has gone through our software. And so it's like you don't realize the impact, and when the other thing is it's much more tangible than kind of like a completely internet-based application, because you see your changes causing containers to move in a facility. These massive cranes are running based on your direction, and you kind of have it's very physical. So it's that's basically why I've stayed in it. It's just such a great area to work in.
Awesome, cool. So, do you manage teams, or you seem to have like a very sort of omnipresent view of like how all this hangs together? Like, what is it specific? Are you still coding? Like, where do you fit in day to day?
So I still code on a day-to-day basis. I'm kind of more like at the technical lead level. So I direct a team of engineers and give them the vision for kind of how we want the direction of this particular area of the product to go. But I do code every day and keep up with it. We run in a kind of it's not I guess ideal, but we are trying to be more agile. We've got a Scrum process in our development team. We have a stand-ups every day. It's kind of this standard normal thing. I think the biggest challenge for our software engineering team is that we have to push against an organization. We have to work in a global organization that is kind of more geared toward like a traditional enterprise, and like they want to define releases up front, fix scope, and then work on the scope, and then deliver a product. And so there's a trade-off between like how much agility you can get within the context. And I don't blame like the company. Our customers are very our customers are very conservative, right? So even if we said, okay, we're going to produce a release every single week, and our customers would not install that release, and so we're basically we have to balance the effort of like trying to be super agile and getting releases out to customers with the need for the customers to validate and test and install, and they have different levels of sophistication in their processes. So anyway, that's kind of just giving you a little bit of background, but we are very forward-thinking about how to program and how to do a better job, and we have some really great talent here, and so here we are.
Great. All right. Well, once again, I want to thank John Scattergood for giving us an incredible overview of how automated the process is for marine container terminals, and how half of the products in your household eventually get delivered through ports to your door. Um, cool. Thank you very much.
You're welcome.